Our guest speaker today is Garrett Rosser. Garrett is a certified energy manager and former energy management consultant. His areas of expertise include programming and reprogramming of building automation and energy management systems to increase energy efficiency, commissioning, retro commissioning of HVAC hardware and software, analysis of interval data and energy provider billing, trend analysis, and utilizing knowledge of mechanical systems to achieve energy savings and improving occupant comfort. Our co-presenter is Gary Olt, and I'm going to transition the mic over to Garrett to do an introduction.
Great, thank you so much. Thank you everyone for joining us. Dallas College has been very pleased to collaborate with Gary Olt of GGO Architects, joining us today to discuss a topic that's moved from the realm of more possibility to that of very real and tangible goal, and that is the goal of reaching net zero operations for our buildings. Like many of y'all, we have seen examples of net zero projects from across the nation, and we've begun to ask ourselves very serious questions on what it would take to move our existing building stock to net zero, as well as work to incorporate net zero operations as a goal for new construction projects. Discussions we've been having with Gary have led to the identification of some very high yield strategies that he has employed at projects across the nation, and items that Dallas College is going to work toward in the coming years. We understand that it's a process, as a lot of these things are, but we believe we can find a responsible and effective way to work toward the goal of net zero. So with that, I just want to introduce formally again Gary Olt of GGO Architects. So Gary, we appreciate you being here and the time that you've spent with us so far and the time in this session. I'll go ahead and turn it over to you to get into the meat of the material here.
So I'd like to thank the sponsors that are not only sponsoring the summit, but also to thank them for sponsoring this presentation. Without these sponsors who are also committed to energy efficiency and environmental responsibility, we really couldn't make this happen. So thanks to all of them. So this is our firm, GGO Architects, and we are here today to talk about the 10 steps to net zero energy. Let me move something out of the way. For new and existing buildings. My information is there as well as Garrett's. You can certainly look at that and follow up with us after the presentation, but I think you also heard the moderator share with everyone that it will be available online, and I think that information will be provided by the university. Okay. So let's get the show rolling. So I want to start with just a couple of things. The reason this is important, this is an older chart. This chart is from 2009, carries out 2035. On the chart, you can see graphically sort of what, it gives you a good sense of what the proportional representation is of each of these fuel sources. Now, this was done in 2009. You can look out to the projection in 2030, and they were really only saying that renewables would account for about 10%, coal 21, natural gas, and you can go right on down the list. Well, what's really true with the new snapshot, this is a snapshot from 2019, renewables have actually outperformed that. We're now at 17%. Nuclear is 20, coal has dropped substantially. Natural gas has actually climbed a bit. So this is another chart that also takes you, this is 2019 right here. And again, it still shows you that the contribution from fossil fuels is still very substantial. And this isn't something, although we're seeing some pretty incredible movement with renewables and an increased dependency on nuclear, you can still see that it's a small sliver, 17%. And we've got a long way to go. So what that says is at least for the foreseeable future, probably the rest of my lifetime, we're going to be dependent on fossil fuels unless we have some real breakthroughs with a lot of things. The wind is wonderful, but where you generate the wind, you can't get it to where you need it because it's just physics. You lose it through entropy. Batteries are going to change that. Solar power, same thing. Generate power during the day. Battery technology is pretty expensive. There's just not a path currently without some real innovation and transformation in batteries before renewables can play a larger and larger role. So the reason that we're talking about the 10 steps to net zero is we have to really acknowledge the fact that fossil fuels are going to play a significant role in generating electricity well into the future. This is another interesting chart that's just graphic, gives you a graphic representation of CO2 being generated by the industrial nations. And you can certainly see how large the United States contribution is. You can see China. India's is growing at a pretty rapid rate. But it just shows you that the most industrialized nations are generating a tremendous amount of CO2. So to that end, the purpose of our net zero game is to reduce the amount of energy a building needs to consume on a baseline basis. We call it passive survivability. Drive down that load that you need to heat and cool a building, light it, provide for plug loads to the lowest level possible. Where you begin is, as I said, passive sustainability. And it really starts with orientation. Most designers, most architects, the vast majority of architects, pay no attention to this. And if you really begin to understand how you can use the path of the sun, summer and winter, natural ventilation, where does the wind come from, plantscapes and so on, you can dramatically reduce the amount of energy required to heat and cool a building, light it, and plug loads to the tune of almost 95%. Typically, commercially, we haven't been able to budget much past 47%, but that's a big start. So in other words, you could say roughly we've been able to cut the energy demand of the buildings that we design by almost half. And I think we can continue to improve that with a number of things that you'll see as we go through the presentation. So passive solar design really addresses, what direction does the building face, talks about shading, natural ventilation, daylighting. If we can implement good daylighting into our buildings so the artificial lighting doesn't have to come on as much, that's tremendous savings. And I'll say it here, but you'll see further numbers. Artificial lighting can consume somewhere around 15% of your total energy demand in a building. So if you can shave a good deal of that off the load, you're making good inroads. When I talk about shading and daylighting, that has to do with understanding how to design proper fixed shading devices, green screens, living walls, trees. Trees are wonderful to cool exposures of the facade that are exposed to a tremendous amount of heat gain, plantscapes to shade spaces. And films is another option, and motor operated controlled shading devices on the windows. So that, what I'm saying there is you can put a sensor controlled shading device on a window, and as the sun hits it, that shading device can actually move with the introduction of direct sunlight. So passive solar really revolves around this. We all know what the greenhouse effect is, and it happens to all of us in our cars. And buildings are not much different than an automobile. Automobiles aren't that much different than buildings. This gives you a representation of how the sun really affects us here on the planet. What's direct, what's absorbed, what's diffused, and what's reflected. This shows something that most people really don't understand. We have an axis, the planet has an axis, we spin on that axis, and then we move around the sun. So that what we get here is we get longer daylighting, we get a different sun angle in the summer than we do in the winter. And here you can see it, summer sun and winter sun. And that simple little formula is how we control heat gain in buildings. Again, very simple chart. But what it does show you is that this is the south. You can see that the primary introduction of direct sunlight is from the south. The north is typically shaded, and the east and west also have an influence. Here in the southern part of the United States, that western sun is a real killer. It's just an energy killer, and just the intense heat of late afternoon is really rough. Okay, so this is very simple. It's surprisingly rudimentary, but it is the most profound chart or graph or approach that you can use to design a building. Small glass area in the north, moderate glass area on the east, major glass area in the west. And this indicates moderate glass area. My design philosophy is I try to eliminate glass on the west to the greatest extent possible. And again, paying attention to the influences that affect your building. Heat gain, wind load, summer breeze, winter breeze, all those things can affect how you design a building. These are building envelope considerations that many designers don't consider. And you can see that these mean heat load, and it's different indications for different things through the foundation, through a window, a low window, through upper windows, clear stories, through the roof, and through the walls. Proper modeling, and we'll talk more about that, but that's really what factors into building envelope considerations. We need to think about designing buildings in the envelope almost scientifically. We can't just throw walls up and windows up and then just try to pump a lot of air conditioning in there and muscle through it. There was an NFL announcer, Pat Summerall, and it used to drive me crazy because he would say, and it was Train, but I support Train, of course, but it was a Train commercial, and he used to say, it's 72 degrees all across America, and because of Train. Well, that's true, and you can do that. You can muscle through it with a great deal of air conditioning or heating, but if you can reduce those loads with your just fundamental building design, you can then begin to reduce the size of that mechanical equipment. Again, here's a solar fundamental. So I showed you the chart of the sun when it's high in the sky in the summer, low in the sky in the winter, and you can take advantage of that. So here's your summer, you shade that window. Wintertime, you let that sun in. And this works in all latitudes across the United States. Here in Texas, what doesn't work very well for us is, or across the Sun Belt really, are skylights, because the sun isn't controlled. It's just driving itself in all the time. You move up north, Minnesota, Wisconsin, Illinois, Indiana, those states across the northern part of our country, pretty much north of the Mason-Dixon line, and skylights can be very beneficial. But this is the graph that we really need to use for primarily designing buildings here in the Southwest, and that's shading out the summer sun, allowing the winter sun to enter the building. So I put this up, and I'm not going to touch on this much. However, this is a great example of passive sustainability. This is Mesa Verde. The native peoples have built this, used all natural materials. The facade that you see faced due south. The overhang above shaded all those facades in the summertime so that all of that masonry would cool off, stay cool during the day and then cooler at night. And it kept the inhabitants very, very comfortable. In the wintertime, the sun angle is such that it would provide direct sunlight to all of these facades, and then you get that intense sun energy that would warm all those masonry facades and keep the residents cool at night when the temperature in the desert dropped. So without mechanical systems, native peoples understood very intimately the path of the sun, the difference in the seasons, the sun angle, how to capture heat, how to diffuse heat or eliminate heat, and create a very comfortable environment without air conditioning systems. So to pull this off, we really need to start with baseline modeling, and I'm going to ask Garrett to jump in with me here and talk about this a bit. But what this is about is, up until recently, we've never looked at, as I shared those opening slides, we've never looked at a building as a holistic functional ecosystem. We've never really evaluated the impact of direct heat gain on the south, or the shading that happens on the north, what happens on the east, what happens on the west. We've never looked at that. We've never looked at insulation. We've never looked at the energy performance of windows or insulation or vented roofs or those kind of things. So to get a handle on this, we have to start doing baseline modeling on all new buildings, and it applies to old buildings too. You can look at buildings and see what the difference is. I was talking with a client yesterday. They bought an old building in Texarkana. The building had $8,000 of energy bills on a monthly basis. They started to look at everything, and they found out that the elevators were ancient, the light fixtures were ancient, the building wasn't insulated, the windows were single paned, unshaded, awful. They made some simple improvements on that building, and they have cut the energy use of that building down to $600 a month. So think about that. So for $8,000 versus $600, that's a monetary description. However, the real issue here is, where does that electricity come from? You go back to that first slide, and I showed you that Primarily, our energy is being derived from burning fossil fuels. If we can take a building and reduce it from $8,000 in utilities to $6,000 in utilities, and I won't get into the engineering of BTUs and all that, but what that says is that's a significant amount of fossil fuel that has to be burned to heat and cool a building. And that's the way we need to look at it. Garrett, you want to jump in and talk a little bit about the kind of things that you're looking at there on campus, on the campus?
For sure. I think baseline modeling for existing buildings and for future construction, I think it helps prevent the tendency or the potential for random acts of efficiency, where people are, get hot on a certain idea and say, okay, yeah, we need that. Well, it ends up, individual strategies don't end up being evaluated, Gary, as you mentioned, as part of a system. They tend to be more just looked at in isolated fashion. So,
sure, piecemeal.
Yeah. So I think for us at Dallas College, we started with some more comprehensive benchmarking, both with some internal portfolio type management in terms of looking at our buildings on how they perform one versus the other on a meter by meter and building by building basis. And we're looking at that, in the past, and then trying to use that for projections into the future for budget purposes. But certainly just from an energy use standpoint, you have to have a great understanding of what your existing buildings are doing, and start to dig into the why are they doing those things, and where do you identify discrepancies. And then we have analyzing cost effectiveness of different measures. If we're looking initially to try and implement strategies that maybe have a single digit ROI, these very high yield projects, we're going to see that on the meters pretty directly. We're going to see that in the billing, and we need to be able to monitor and track that. And then as we start looking at some more sophisticated projects or trying to identify a strategy that we might want to start on a small scale, but then evaluate to roll out on a larger scale. I think you've got the tools like DO2, Train Trace, some really more sophisticated modeling, where we're entering some baseline data on the building construction and the energy usage, and using that to really say, okay, what is going to be the costing impact of the entire life cycle of a change to a building, and use that to make some really well-informed decisions. And down below here, we've got some some goals here. This was based on a 25,000 BTU per square foot goal, on an all-electric building, where things might come out. And your buildings will be different. But for Dallas College, we're looking somewhere in the 1.6 to 1.9 watts per square foot as an average monthly demand, and your distribution of HVAC lighting and plug load will be different on different buildings. But that's some kind of generic guidelines that would be, aggressive to try and shoot for to set up a building for on-site renewables.
And Garrett, it wasn't that long ago that we were looking at buildings that were consuming 8-10 watts per square foot. So we've come some way. So let's talk about individual building components and aspects of a net zero building. As you saw on one of those slides I showed you at the very beginning about the direct impact of heat gain from the sun, the largest surface, this is in the Southwest, it's also true in the North, is from direct solar gain from the sun on a roof. And what's really been proven out is that 75% of the direct heat gain can be radiated through proper roof design. So if you start out by getting rid of 75% of that heat gain, then you only have to deal with the last 25% to cool the building. You can get up to as high as 95% if you go beyond insulation, where it talks about increased insulation here, minimum R42. Code is not quite at R42 yet, but there's also the thing about insulation, there's a sweet spot. You can over-insulate, and it isn't going to do anything more for you. You can over-insulate walls, and it really isn't going to do much for you. We've sort of found that, looking at it today, the way we're working, R42 is about the sweet spot in terms of affordability and offsetting direct heat gain for the roof. And you don't need much more than an R13 wall. You can go up to R30, R26, and with some of the open cell spray foams and closed cell foams. And that's really all that you need to do. The other thing that we've been doing that now has been adopted by code is for 30 years, we've been wrapping our envelopes with 1 inch of insulation outside of the sheathing, because you still get thermal conductivity where all the framing is. And by adding that extra 1 inch outboard, wrapping the envelope in that, that also seems to make a tremendous difference in terms of having a high performance envelope. The insulation can be under the roof deck or above the roof deck. There are different strategies there, and I won't get into the specifics of how you do that. That's more of a design situation. Then under reflectivity, you're going to talk about the solar reflectivity index of the roof itself, which means the ability of the roof through emissivity to re-radiate or reflect that heat gain. And when you start to move to a 0.95 solar reflectivity index, it's telling you that generally the vast majority of that solar heat gain is being re-radiated. Cool roof design where you ventilate the roof. Imagine an umbrella, if you could put an umbrella over your building, or as you see a lot of folks do in the South, carry an umbrella out in the sun. That umbrella, if you will, really can cool down your roof. Trees are a good source of that, but the problem with trees is when you get them too close to the building, you can have issues with roof. The other problem is trees drop their leaves, and unless you have regular maintenance, it can be problematic. So there's trade-offs to all of this, but a simple thing to do is you raise the roof membrane, the roof itself, about 1 inch off the deck, and then you ventilate that so that air can move under that. You create a thermal siphon, and air moves under that roof, and it's pulling that heat out and away from the interior, and that's how you can get to 95%. Another strategy we've used are living roofs, and we use living roofs to good effect. If they're designed well and installed properly, it can virtually eliminate all of that heat gain from the sun. Here's an example of a fully integrated roof that's designed with optimized roof insulation. This has R42 roof. It was a lightweight concrete insulated system. This was an old building, heavy masonry building. We were able to do that. You can see we've introduced daylighting through skylights, and we've integrated solar panels on this roof for renewables. And I can talk more about this building later. And in the distance, you see the mechanical systems that were also integrated into this building. And this is very high performance equipment. Garrett will talk about this a little later. So what's fun about living roofs is a friend of mine distilled it distinctly and said, birds don't like to land on hot shingles or hot roofs, or even the roof I just showed you, because they like to land, and insects like to hang out on the living mantle of the earth. So imagine what a living roof does is you're building a building, so you're cutting out the living mantle of the roof, and you're putting a building there that's a heat sink that has heat gain and just warms up and heats up. If you consider the possibility of just cutting out that mantle and lifting it to the roof, well, now what you've done is you've replicated the living mantle of the planet, and you've put it on top of your building, and it works to mitigate heat gain incredibly. These are some bus stops that have been done, so they create a very cool environment below the roof, and they have it as a living roof. They did that utilizing a living roof, and so it has multiple benefits. This is in San Francisco, beautiful building. And again, this building is roofed entirely with a living roof.
Gary, I just wanted to hop in and add some Dallas College perspective. During last fiscal year and through the end of this fiscal year, Dallas College will have added 615,000 square feet of high reflectivity, high emissivity roofs, and bringing all of that insulation up to code, which currently is R25. But some of our original roofs across some of our campuses were just OSB with copper on top, and so that probably had an R value of about 2 or 4. So there's some significant opportunities there, and again, we have made a commitment to replacing those roofs with just really high performing materials.
And Garrett, that's a good point, because that's a significant investment, and it's also a significant response. You have a rule of thumb that you could share in terms of, as you've replaced those roofs, what have you seen in just energy consumption as a product, or I guess as a portion of the total?
Yeah, we don't have good data yet. A lot of those roofs, again, are planned. Some of them are just a few months old, so we don't have great data on what the effect is, but we're very optimistic about the work that's been done there.
And again, you and I talked about modeling baseline and benchmarking. Once you're able to benchmark what those improvements have yielded in terms of energy savings, it helps to cost justify future and more aggressive projects. Minimum specifications. This is window and glazing systems. The biggest problem we have is in older buildings, 20, 30, 40, 50 years old. The window systems are shot, generally single glazed. The frames are gone. You're getting a lot of infiltration, exfiltration, and you're losing a tremendous amount of energy through the windows. So with a new building, you've got the opportunity to do new windows. And the minimum specifications would be, as you see here, in terms of the U value, which is the insulating value, the shading coefficient, high performance glazing, and then of course thermally broken frames. With an existing building, there are things that when they are scheduled for replacement or failure, you would meet these specifications. But let's say you've got a system that's, it's not, they're not totally shot, but they're on their way out, they're kind of like late middle age but they're leaking. Well, there are things you can do. You can go and replace the seals on the storefront windows. You can make sure that caulking is installed properly. With older buildings, now we do a lot more with sealing a building up, making sure the envelope is wrapped and sealed so that air can't get in. Older buildings, not so much. And so when you've got a sealant joint around a window and that sealant joint fails, that's a direct path for hot, humid air to find its way in a building. Buildings operate generally, older buildings, the negative pressure, you certainly want buildings to operate in positive pressure. But a lot of the older buildings operate negative pressure, so you're drawing in all that hot, humid air and or cold, dry air in the winter season, and that can really mess up your energy performance and the optimization of mechanical systems. So a window system that's not quite due to be upgraded or replaced, at least make sure the seals are good, and that's an easy thing to redo, and or seal any open or broken down sealant joints. This is talking about shading, and I talked about it previously. Think about shading with windows. There was a study done in the city of Austin by A&M. I think it was in the 70s. And it might have been the 80s, but they looked at if they replaced every window in the city of Austin with the most expensive window you could buy, triple glazed, gas-filled, low-E coated windows. How did it compare to just adding shading on the south and west sides? Strikingly, what they found was that a single pane window with the proper shading outperformed the best window on the market that you could buy by a factor of 4. So the simple thing is start with shading, then put in a window that's cost effective in terms of and usually just an insulated window, as I said, with the specifications we had on the previous slide, that's thermally broken. You're going to have probably the most optimized window and glazing system you can provide. This is a simple chart that we've developed over the years. It's tweaked a little to get the ideal winter and summer sun angles and how to protect those glazing systems to, again, take advantage of the low winter sun for heating and shield the interior from the direct solar heat gain in the summertime. So it's that simple. Here's an example. You can see the upper shading mechanism. There's a lower shading mechanism. This is due south. This is the interior in the middle of July when the sun is very intense and very hot. Another aspect of shading is on the east. Too often designers don't pay attention to the sun coming in on the east. Where the eastern sun is a problem, it isn't so much heat gain with eastern light. It's more a problem of glare coming in and making an office difficult or a classroom difficult to work in because the glare is so intense. So this was the solution that we came up with. At that low morning angle, the sun comes in, hits these baffles, and throws that daylighting up on the sky, or on the ceiling, I'm sorry, and illuminates the ceiling with natural daylighting. So you can see that this is all naturally daylit space, and the lights are not on, and you can see that the foot candle level is sufficient for close work. So that reinforces what I'm saying about proper proper design on the building envelope, you can virtually eliminate the cooling required to offset direct solar heat gain, and also the load from lighting that has to be on when the sun's shining. Here's another example. This is on campus. There are two kinds of shading devices shown here. This is a direct shading device. That angle is about right to shield this glass. It's solid over the door. You want to think about rain protection, that sort of thing. These vertical blades actually do serve a purpose, and they block that low-level eastern sun for glare, and or they block that low-level western sun, which is also problematic. So there are, and I don't have a plethora of options here just to show you. This is just to give you a general idea, but we've innovated hundreds of different ways to shade a building properly. This is another example. It's on campus, and you can see where heavy thermal mass was used to block the sun. And again, here are some sunshades. This one's probably more decorative than it needs to be because there's really nothing there to shade, other than it will keep this wall a bit cooler. This is another shading device we finished recently, our firm finished. This was direct south sun right here. This is a tennis center. The building is just finishing up. We needed to shade that sun. We looked at a number of ways to do it, and the one that our user decided on was this one, which was very whimsical, where we took steel plates, folded them, we did the graphic, and we perforated the surface of it so that it diffuses the sunlight. So all that comes through these south windows is diffused light, and we have knocked off, again, the direct solar heat gain. This is another building on campus, and this is at Richland. This building I really enjoy because the quality of the daylighting is amazing in here. This is the facade that was shaded that I showed you some of the sunshades on the other slide. These are skylights up here, and they're diffused, and you can see how the natural light comes through. The lighting is on, and I've been told that this would not be normal. It was done for the photograph, and typically those are tied to sun sensors so that they would normally, during regular operations, these lights would not be on because they're just not needed. So again, it's another case that supports the fact, shade out the direct solar heat gain. If you shade properly, you can introduce that natural daylight into a space so that you've reduced your air conditioning load and you've got wonderful daylight to illuminate the space. And I'm going to segue, this is not really a 10 steps about energy efficiency, but what's really true is that there's more and more discussion about biophilic influences on the human species. And it is true. Humans respond to daylight so much better than they do in a space that's artificially lit. Here's another space. It has windows on both sides. This is south, this is north. The north shading isn't as important. I don't believe there's shading on the south facade, but if it did have it, this is another good example. Again, the lights are on here, and I think it's just a function of the controls that were just not operating on that day. And again, you can do things CalWall. This is a CalWall system. CalWall brings in natural light and offsets all the heat gain, and you get wonderful daylight. This is the skylight from the interior that I showed you previously on that roof. There was no daylight in this building. It was an old warehouse. So we simply cut out sections of the roof and introduced the daylight with these. These are triple line skylights. But these work, and CalWall actually works because the way the systems are designed. So again, you can see that proper design of the glazing systems can provide wonderful natural daylight, offset the need for artificial lighting, and deal with mitigating or offsetting that direct solar heat gain. These are some other examples I'm going to show you real quickly. This can apply to new buildings and, of course, old buildings. If you've got an old building that has a facade that isn't shaded properly, these are simple cables that run up the building. It's planted down here, and this is a green screen. It's a living green screen. It has multiple effects. It knocks down the direct sunlight from the sun, so you get diffused light. But what it also does is plants are amazing, just like a living roof, at absorbing that heat gain from the sun and creating a cooling effect on that facade. So the point I'm trying to make is when we design buildings, we need to think holistically. As Garrett said so well, you can't take piecemeal examples. However, if you've got an existing building, certainly you have to approach it one piece at a time. and these are simply some more living roofs. So I've sort of touched on this already. Artificial light sources. We need to utilize LED technology, eliminate all high wattage lighting, get rid of old lights. Old incandescent lights are virtually just energy vampires, just sucking all that energy away. And then targeted prioritization. So this speaks to what I said earlier, is that identify what the use of the space is, determine what your foot candle levels are, introduce natural day lighting, and augment with artificial lighting to the extent that it's needed, but not much more. This is an integrated example. This photograph shows you that we have natural day lighting coming in. This is on the south, it's shaded. This is a light shelf to throw natural day lighting in. I was sharing with Garrett the other day that all of these lights are photosensors. They have photosensors to sense how much daylight is in the classroom before they come on. Each row is operated individually. This room would have had far better natural day lighting. Our original design had this light shelf coming into here, about right to there, to illuminate 3/4 of the room. Well, for budget purposes, that was cut back, and it's because it's a difficult thing to cost justify. Well, then it was. But I think, again, that goes back to the modeling. Take a look at, hey, if this eyebrow costs this much more, what are the long-term savings of offsetting the artificial lighting using the day lighting over a 20-year period, 30-year period, 50-year period? If it's a municipal building, you've got an easier road to make that financial case than you do with a commercial building where they're trying to amortize their costs in 5 to 7 years. Here's another example. This is that tennis center. This is all south-facing glazing. There's no glare. You can see the natural daylight, and these lights are on because we're testing them. But this is going to be a retail area. And so here again, the lighting is just a supplement when we don't have proper daylighting. Garrett, I'm going to hand the baton to you to talk about HVAC systems.
Sure. I'm going to pause real quickly here. I put my email address in the chat. Hopefully everybody see that. If you need to step out, participants, and go to another session, or if you have other obligations, so you can send some questions my way. We'll do our best to get those answered back out to you. Since we did start a little bit later, we do have the go ahead to keep going, and we still have some more content to cover. So we're gonna keep rocking and rolling. And so if the participants you've stuck with us thus far, if you want to stay on with us, we would appreciate it, and we'll continue covering the content and make sure that we've got this recorded for anyone who might view it at a later date. But we'll go ahead and work through it in its entirety, maybe a little quicker, but we'll keep rocking and rolling. So. All right, HVAC. Again, there's a lot of discussion. This is the energy hog on most buildings, particularly in our climate zone. And the strategy for us is to upgrade and replace, or on new construction, specify the highest efficiency equipment that we can. And certainly there would be some trade-off there, but and generally the idea is you can have a great new building envelope, you can have a great new piece of equipment and still use it poorly. So nameplate efficiency is not the end-all be-all, but if you start with a great piece of equipment, you're set up to be in a good position. A couple strategies here: DX equipment for all 24/7 zones. We have an extensive IT project where all IT spaces that were not did not have existing DX direct expansion air conditioners are receiving those. We have other 24/7 operation areas that will be moving to DX as well. So that's good, getting those large pieces of equipment turned off and having some very specific HVAC for those areas. Upgrade or replace existing controls, VFDs. Again, these are things that are pretty standard stuff, but it takes a while to work through. When you think about 4.9 million square feet that is Dallas College, there are a lot of devices to work through. High efficiency equipment in terms of chillers and their controls, boilers and their controls, and also looking at the use of VRF. It kind of got a bad rap as it was rolled out in the industry. But I think if, the installation is correct and we're using brazed joint connections on all refrigerant piping, and you follow the manufacturer recommendations, some of them require that you do not use a sight glass, that you do not use filter line dryers. So that is a deviation from kind of the norm on DX installations. And certainly all you techs out there have to be charged positively with nitrogen. And increasing fresh air from and being intentional about how we do that is one thing. Making sure we've got accurate CO2 readings, that sort of thing. And then something that's really come up recently in the last 6 to 8 months, filtration. And we think that certainly for our environment, ultraviolet treatment and bipolar ionization are options that we need to be evaluating and determining how they fit in our overall strategy. We've got a couple pictures of some devices here, Gary, if you advance it forward.
Oops, back. I'm sorry. I hit it too fast.
Okay. This is a brand new cooling tower down at our Mountain View campus. Again, shiny and great, and a definite upgrade over the existing unit there. It's going to have improved heat rejection capability, VFDs on all the large motors there, and just sets up the campus to have a good serviceable piece of equipment that is high efficiency. The next picture is a chilled water storage tank, also at Mountain View. And from an energy usage standpoint, chilled water storage allows us to displace some of that load to overnight. Gary, can you hit us one forward there?
Yep.
Okay. So chilled water storage tank. Again, when we start thinking about renewables, if we can displace some of the load to overnight, that reduces the amount of that you might need during the day when the building is fully occupied. Additionally, in chilled water systems at night, the heat rejection is more efficient, more effective overnight on water-cooled systems and air-cooled systems as well. But water-cooled as the system that we have down there at Mountain View. These are some condensing boilers. We've got a few shots of condensing boilers. That's our standard now across the college, that any boiler that's replaced is going to condensing. High efficiency. Most of them are 5% efficient or higher due to their condensing ability. So really great options that for a lot of folks have become the norm. And for us, they're becoming real workhorses for us. This next picture is a rack of VFDs. Of course, we've got VFDs on all campuses, on all different types of equipment. There we go. This is at Richland campus. And so a whole rack of VFDs there. Again, we've had several in service on our various campuses for 20 plus years. And that's a real staple of energy efficiency if they're used well. We have seen inappropriate application of a VFD where the control is not really used in any beneficial way. That is that the motor may start up slowly, but then go to 100% capacity and stay at that level. That's not the purpose of the VFD, and you're really missing out on some opportunities there. So matching controls with the equipment is the best way to maximize that. Here's some brand new condensing boilers at Brookhaven campus. Again, gorgeous installation. I get excited about that when I see it. But at the end of the day, this is going to be equipment that's going to be with us for a long period of time, and it's going to, in the long run, provide some great savings. We've got a magnetic bearing chiller here offered by York, and very effective machines, extremely low friction on the centrifugal compressor. And they're becoming more and more prominent in the market. And again, this one is at Brookhaven as well. The next picture is at the Richland campus. And straight ahead in the middle of the picture is a retrofit device by Trane. It's called the Adaptive Frequency Drive. It is a VFD for that large centrifugal chiller that's behind it. And again, that was a retrofit coupled with some more advanced controls provided by Train to make that machine even more efficient. All right, and the last couple of pictures we have are of VRF systems. Again, this particular unit is referred to as a cassette. They have some wall mount units for the interior usage. And again, we've got a filter device and a small interior fan. And there would be multiple of these spread throughout the building. You can share heat as it is across the system. One portion of the building may be in heating mode, the other portion may be in cooling mode, and you can balance those heat flows out through these VRF systems.
And those are the condensing units that you see there. Weatherization. So this is, again, what I was talking about, weather stripping doors and windows. This is more applicable to older buildings that have been in service for quite some time, and sealants age. So over time, a regular maintenance program needs to go through and weather strip doors, window systems, upgrade or replace door sweeps, astral storefronts, aging, sealants and caulking, openings, mechanical penetration, open gaps, pathways, cracks, and so on, because this really can affect the overall energy performance of your building. You've got a building that's just leaking conditioned air with no control of that. It undermines the operations of the mechanical systems as well as just straight up energy loss. To the extent that once you really create these great systems of lighting, fresh air management, lighting controls, new HVAC equipment, and so on, again, it's all for naught if things aren't maintained. So again, I'm going to pass this back to Garrett to talk about the kinds of things that need to be done in terms of software that controls the building systems, and then regular maintenance to keep the systems operating at their optimum levels.
Yeah, for sure. As many of you know, Dallas College has gone through a reorganization from 7 individual campuses into a more cohesive college, moving all in the same direction. And with that comes the opportunity to unify our strategies on energy management and take good things that had been happening across all of our campuses and really pull those together into a cohesive methodology for making sure we're using resources well. There are some opportunities for sure that are out there. Lighting control strategies and HVAC controls, a lot of them are software driven, some of it's hardware driven. On HVAC controls, big one is consistent set points, and I'll mention again here in a moment. Optimized sequence of operations. Okay, there's new guidance from ASHRAE on Guideline 36, which provides some recommendations on high performance sequence of operation. Great resource. Economizer controls. We already talked about the impact, potentially negative impact of bringing in too much outside air. But a lot of folks miss out on the opportunity for economizing in North Texas because they say, oh, it's Texas, it's hot, we don't need, it doesn't make sense to have economizers. Well, particularly for the institutional environment, we tend to have times, even in the winter, where we have higher heat load, whether that's equipment or a high number of bodies in an interior space. So economizers, we still take advantage of hundreds of hours a year of free cooling through economizers. And CO2 management, again, that's just making sure that your CO2 sensors are in good shape. And then you have great set points. There's some misunderstanding of ASHRAE Guideline 62 or Standard 62, and that is 700 parts per million above the baseline CO2 level is where your set point ought to be. So for us here in Dallas, that's somewhere in the 1,100 to 1,200 parts per million. If you wanted to run it at 1,000, I don't think you'd get too much argument from me. But 1,100 to 1,200 parts per million on CO2 is a great starting point there. And then regularly scheduled maintenance. Okay, make sure the equipment is working well. And kind of the last couple items, commissioning checklists for PMs, preventative maintenance work on equipment. That's going beyond just changing filters and greasing motors. Those things have to happen, but we need to be very intentional about how we exercise equipment, make sure chill water valves are functioning properly, make sure dampers are functioning properly, ramping fans up and down. Not only do we want to see the equipment respond, we want to see the correct response from sensors. We want to see when the fan ramps down, we want to see the pressure sensor drop and that sort of thing. So that's just taking your maintenance and becoming a little bit smarter about how we do things. And then the last, implement campus-wide 6 core strategies, and these are ideas that have been implemented at various campuses, but we need to get rolling everywhere. And real quickly, in class equipment scheduling, right? Turning things off when they're not needed, matching our schedules with the class loads. Second one, consistent space set points. Third, equipment staggered start. That is avoiding startup demand peaks. Equipment capacity control. If you've got 2 chillers for redundancy on a building and they're sized such that one machine can the load on a building, you don't want to ever see both machines load up and start up together, right? They should be on that proper sequence. So making sure the correct equipment is selected for the correct load is a great strategy. 2 more, proper equipment maintenance we just talked about, and building automation operation. And that is relying on these intelligent controls. Too often, building operators put rides. We want to get away from that because we're putting band-aids on these items that we're having to go back and revisit maybe seasonally. So if we let the controls do their work, we can identify where we have breakdowns and failures. Not only is it going to improve energy efficiency, it's going to improve occupant comfort.
Right. One thing as we move to the next slide that I'm going to mention about the CO2 management, it's primarily to control the quality of fresh air, but when you think about it, if you've been in an auditorium or a classroom that's designed for 165 people, there's 5 people in there and everybody's freezing. That's because when buildings are designed, there's a CFM, fresh air requirement per person, that has to be provided to that space. Most engineers will design that fresh air makeup for 165 people with no controls to drop it down to the fresh air you need when there's only 2 or 3 or 5 people in that room. That's what those CO2 monitors do. They monitor the amount of CO2, and if fresh air is not needed, then it's not generated. So you're not using energy to create conditioned air for 163 people that aren't in the room.
Great. Here's a picture of a Trane centrifugal chiller, again with a factory installed adaptive frequency drive and the controls, sophisticated controls that go along with that machine. So a very high performance piece of equipment. I think we've got another shot of it from a different angle. These machines have served us well. And the technology, really has come such a long way, and it opens the door for more refined responses in terms of central plant optimization, where we can start looking at variable flow, certainly on the secondary side, primary flow, and even variable condenser water flow. And Trane has a great engineering newsletter on that subject of variable plant flow. And then here's a relic of our existing systems, which we still find in many buildings here across the nation. That is pneumatic control. And at the time, it was state of the art, and these have had a great service life, but they need to go away. There's great opportunity in making sure everything is on direct digital control and being able to really refine control between systems. Again, it goes back to having a more holistic approach on controls rather than each component doing its own thing. DDC, direct digital controls, facilitates that, device level and then system level and then even building to building level communications.
And just more controls.
Yeah, gotta love our VFDs.
Lighting controls, I think Garrett's pretty much covered that already. But what's important are additional things like occupancy sensors, light harvesting sensors that we spoke about, sun-controlled shading devices, occupancy schedules that match the calendar and program use. And then I did touch on the impact of biophilic design and what's becoming an even greater influence now is diurnal lighting patterns. We're not there yet, but at some point, light fixtures will mimic the colorization or the effect of sunlight. As sunlight moves through the course of the day, it changes. As a species, we've evolved waking up in the morning, going to sleep at night, and the quality of that light has really affected how we, our mental acuity and so on. Occupant behavior, this is the other thing that really can make a huge difference in how a building consumes energy. And we want to begin to talk about what is that occupant behavior? And we need to talk about implementation of plans between occupants, users, facility managers. Typical example is perhaps an office space or a dorm room or something where someone has a space heater under the desk, and they have, toasters in the room. They have a whole bunch of other task lighting, just a lot of additional plug loads that can really drive that load up. And some of that can be offset by just simple educational programs that say, look, hey, don't have your heat on and the window open. So it's as simple as that. And working on plug loads to control them. Garrett, do you want to add anything to?
No, just particularly for Dallas College, this is a major opportunity for improvement, and again, it comes back to unifying all the campuses, unifying our processes. There's been so much emphasis put on making sure we've got the right classes to meet the needs of our students, and we get the right personnel in those classes to meet those needs. Now, on the facility side, we need to make sure that we're interfacing well with those other portions of the organization that are helping make those decisions, so that we're really working together to make the best decision on how to utilize resources. And again, it goes back to education piece. It goes back to having folks that understand general principles about mechanical equipment and how they're used and what the impact is. And just making sure we're choosing appropriate spaces for the function. So much emphasis is put on the operations side, and the operations folks and facilities folks have a great impact on energy usage, but so do the occupants. And we need to work more towards marrying those business functions that traditionally in many organizations tend to be separated.
Mobility integration. This is, again, something that we can do as designers to make it or create spaces that accommodate things like bicycles. And if you can encourage students to use bicycles to get around campus rather than using other forms of transportation, that's sort of a campus-wide thing, but and not really affecting the building use, but overall campus energy reduction. Wellness integration, again, this is a little outside of the 10 steps, but as we just talked about how behavior can affect energy consumption in a building. If you create some wonderful public spaces that are shaded properly, that have plants, give students and staff members opportunities to connect with outdoor spaces when the weather's nice. They're not going to be sitting in a room with lights on and that's perhaps too warm or too cool, and encourages them to go outside, enjoy the natural environment, and take advantage of natural conditions. We're going to kind of close on renewables here real quickly. And as it says there on the slide, to achieve true net zero performance beyond a highly optimized structural envelope, it's going to require the use of energy generated by green, non-fossil fuel sources. So when we began this presentation, I showed you the challenge of only 17% of our energy generation comes from renewables. Well, this kind of shows you the distribution of renewables and what's growing and what's going to continue to grow. And you can see that wind generation is going to grow at a much faster level than solar. But it's just something to consider that once the primary purpose of getting the 10 steps to get to net zero, we're trying to get to net zero. And then whatever the energy demand is, the residual energy demand, we need to offset that with renewables. These are on campus. These are freestanding solar panels. Just shows you the controls on the rear side. And I think what's a very strong component of any renewable program is to educate the users and participants to understand what's going on and what these systems do and what they're offsetting. I really like to use real-time monitors that can tell you how much energy is actually being generated and how much fossil fuel energy is being offset. This is an example of that other roof that I showed you, and you can see how we integrated the high performance VRF systems and the solar panels right on the roof. Integrated design, planning and design, design spelled wrong, is all about to achieve the kind of things we're talking about to get to net zero. You can't have everyone working in their own little corner in a non-integrated system. The entire team, staff, architects, administration, engineers, contractors, subcontractors, all need to be on the same page, working together to innovate solutions to reduce the overall energy demand. What are the ideas that you can do? You know, if you need glass on a western exposure, all right, well, what can we do? Well, let's do a green screen. All right, if we're gonna do a green screen, what are we gonna employ to do that? What sort of design solutions can we generate to make that happen? But then you've got the contractor who says, oh my God, that's gonna cost a fortune. Well, okay, is there a less expensive way to do it? And that's why integrated design is so important, rather than, as we have for so long, a very segregated and divisive process. And one of the last things I want to talk about was just the simple fact that the campus, Dallas College, is growing trees on campus to replace those trees that have aged and to continue to add carbon sequestering methodologies to the campus. I think that's nearly our last slide. The thing that I wanted to talk about with trees, we've got time for a quick, I'll make the story very quick. There was a campus in England, and it was Oxford College. They have very strict preservation standards. One of their larger halls, the major roof beams had dry rotted. After almost 1,000 years, they were no longer structurally sound. And wood has a lifespan, it just does. So they need to be replaced. And the architects come up with steel, that was rejected. They came up with steel clad in wood, that was rejected. The campus and the UK mandated that wood beams of that size go up there. And the architects and everyone involved, the team was like, well, they don't exist. Wood doesn't grow that large anymore. We don't have anything like that. We cannot get the size of those beams. Well, the campus forester was in the back of the room and he was chuckling, and everybody's kind of pointed at him and, what, you think this is funny? And he said, no, I got your beams. And everybody's stunned. You could hear a pin drop. Everybody's like, what are you talking about? You've got our beams. So he called them out to a forest that they had on campus, where he showed them the architectural specifications from 1,000 years ago that said that they need, as they put up those beams, they needed to plant a forest so that 600 to 1,000 years from now, when those beams need to replace, those trees would be standing on campus to be harvested and replace those beams. And they had gone through the calculation how many trees they would lose to freezing, insects, all the things that can happen to trees. And sure enough, there were the proper amount of trees was there. They harvested them, made new beams, put them up, and replanted the forest. So that's an interesting, I think, response. And if we're going to talk about true sustainability and net zero, that's the kind of holistic thinking we need to employ with our efforts to design buildings. And with that, I'll close. And Garrett, I guess we'll take a few questions, or I guess we can. I don't know how to get to the questions unless I stop sharing the screen.
Sure. Our moderator is going to tee some up. He has received some in the chat, okay, and I can see a couple here. Do
we want to leave our sponsor page up, or?
Yeah, you can have that up, and that's great, and people can view that. We'll kind of wrap it up and try and have a hard stop, I believe, here at 12:30. Thanks for everyone for sticking with us. We'll try and get through some questions. If not, again, I've got my email address out in the chat, Garrett Rosser at DCCCD. Actually, Gary, if you could go back to that slide that has contact information, probably is the better thing to have up right now. Let's do that. if you need to reach out to Gary or myself about the content or other plans or things that we might not have touched on here, but you're interested in, feel free to reach out to us.
All right. Thanks so much for that great information, Garrett and Gary. We do have a few questions. And so we'll start. The first question we got was from Nicholas, and he says, I like the sun illustrations. What book is that from? So there's quite a few of the sun illustrations throughout the
That is an old book. You know what? Is it in? You know, there was there's a book called Passive Solar Energy, and I think it was produced in the late 60s, early 70s, and I think that's where that graphic came from, if I recall.
Still extremely relevant.
It is, isn't it? Isn't it? That 50 years ago.
Absolutely. Next question from Valerie. About plants. Do plants damage the facade? She said once an insurance company would not insure her home because of the vines on the house.
Yes, that's true. Vines are problematic because fig leaf ivy, any of the ivies, their root systems can actually work their way into the grout joints and or under siding and or behind siding or through a little pinhole in a sealant joint, and they can cause major problems. So while it looks great, vines growing directly on a facade, yes, that's problematic and you don't want to do it. The nice thing about doing green screens is it is an independent structure that's separated from the wall, from the facade, and so it grows up independently of the actual facade.
Perfect. Thanks so much for that. Next question. This one is for Gary. First of all, they said, thank you for this great information. This is from Beth. She says, my home also uses solar panels and changed or added the insulation to the upper ceiling. The room temperature is really improved, certainly. However, the green grass roofs need to be mowed by person routinely, and safety is concerned. So any thoughts on those green grass roofs and maintenance associated with them?
Green roofs, yes. Roofs that are grass, like the San Francisco building you saw that has a green grass roof, and there's several other examples. There are grass species that you specify that will only grow to a specific height and stop. We've done roofs with natural grasses and things like that, and you don't mow them. You just, once a year, you go up and clean them. What normally has to happen is you saw there's a border around that, the San Francisco project. So it really is driven by code, whether you have to do a handrail or you do a distance from the edge of the parapet and or parapet. So again, that's a code issue. But you don't have to use grasses that have to be mowed. There are a number of grasses that will stay very low. A fairway grass on a golf course, you know, it'll grow to 6 inches and stop. So it just depends on your region, how much water, how the roof is designed, and the kind of plant that you choose, so that you don't have to go up there. You know, you can. I mean, Howard Garrett did a living roof over his addition to his house, and he's got a little hand, you know, push board. He goes up there and he mows it. And I tend to go more toward designing roof systems that just have to be maintained once or twice a year and don't require that kind of maintenance.
Great options there. This final question is directed to you, Garrett, and that says that does Dallas College have any plans to add the grass on all of the existing buildings to reduce the energy consumption in the summer across all of our campuses?
No, at this time we don't have plans to, in a sense, retrofit roofs to green roofs. That may be something that might feature, say, of a freestanding parking structure. But kind of as Gary had mentioned, from a maintenance standpoint and just the commitment to make sure that that system maintains working as intended, I think that's something that we're going to have to be pretty cautious about and make sure that we have something that is going to serve the college well beyond the individual to make that decision. So that's what we're always trying to think about. You know, what are the impacts now of what we do 20 and 30 and 50 years from now? Because these buildings, a lot of our buildings now that we're currently occupying and using well, are upwards of 50 years old. And we expect that they're around for longer than that. So,
And to Garrett's point, it's very difficult to put a living roof on an existing building, unless it's a high masonry building, something like that. It's much, living roofs really require a holistic approach right from the start of the design. If it's a concept that wants to be introduced, then all the systems that go into supporting it, maintaining it, all have to be factored in. What we do know from the living roofs that we've done is that there is a great deal of analytical data that's been collected that shows that a typical life of a roof is about 25 years. Sometimes you can get a little longer, but around 20, 25 years. And living roofs, if done and designed properly, can double that lifespan because the membrane is underneath, not exposed to UV degradation or the extremes of expansion and contraction. So there's a benefit to that as well. But if they are not designed properly, not constructed properly, they are a pain in the place where you sit.
Well, thank you so much, Garrett and Gary. This has been an extremely engaging and informational session. Even as moderator, I'm taking so much away from this experience. I encourage all of our participants to definitely take down the information that you see on your screen there. Both Garrett and Gary have graciously allowed you to ask any further questions to them in that way. We also want to encourage you to visit the summit exhibitors between now and 12:50. So definitely take advantage of the time that we have before the next session starts. And again, thank you so much, participants. And thank you, Gary and Garrett, for your time today. Again, this has been just an amazing session, and we look forward to learning more.